The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Good morning. This is Ruben Corbelan, delivering the ArcFlash hazard analysis options. This is a very interesting seminar with a lot of very good practical information. If you're doing any ArcFlash hazard analysis, you'll be able to start using this stuff right away. It would take about 1 hour and 40 minutes to go through a lot of this stuff. So it's a long time to be in front of a computer all the time. So we're going to have a break somewhere in the middle of this presentation. And at the end, I will leave the presentation open for questions and answers. If you have the panel in front of you, you will see that you have a little hand. That when you click it, I will know it, and I can activate your microphone in order to ask the questions. Okay. ArcFlash hazard analysis. This is not a basic course in ArcFlash hazard analysis. We assume that you already know a lot of the different terminology of what is the ArcFlash incident energy, the arcing current, and stuff like that. We're going to be explaining a lot of that terminology. This course basically is geared to people that have already done ArcFlash analysis, and they have some questions about the different options that that you can consider for the analysis, because there is a lot of different options. This is the content of the seminar. We're going to have a brief introduction. Then we're going to step right into the different options: line side versus load side calculations, maximum arcing time, motor contributions, current limiting devices, working distance, busway model, effective distance, effective raceway. Those are the things that we're going to be talking. This is a practical engineering course, very little theory. It's practical information that you can use performing your ArcFlash studies. Okay, if you have one plant and you contract 10 different engineers to do an ArcFlash study, you pretty much are going to have 10 different results. Why is that? Because there are many options when you perform the ArcFlash study, and there are many scopes also. We already had that seminar. For some of you probably were in the scope seminar and how to do the survey and the scope of an ArcFlash study. Now we're going to be concentrating more on the options, okay? So if there's so many different scopes and options, definitely the results of the 10 different engineers are going to be very, very different, okay? So everybody's really kind of confused. Fortunately, I understand that there's going to be a IEEE standard created to give a little bit more guidance on the procedure for doing this ArcFlash calculations. So they're more standard, okay? But for now, there isn't. So we have this options. You have different doors. Which are the options? Which options you're going to adopt? So that will be an open door that you have to get into. And there's some other options that are no, that means that you're not going to open the door, you're not going to put a lot of effort satisfying that option. So which doors to open and which door just leave them closed? Well, some of the options that you can take in the study, it will have a very large effect on the result. And definitely you should consider those options. Some other options don't. They have a very small influence in the final ArcFlash incident calculation and result. And therefore, if you have a lot of budget and a lot of time, you might include them, but it's really not necessary because it increases too much the expense for a very little gain in the result. Okay? Let's start with the first one, the line side versus load side option. This option is one of those that are very, very important to consider. You definitely have to open this door and spend some time and effort considering if you're going to give results in the line side of main overcurrent protection device or in the load side. The option of choosing the line side ArcFlash incident energy or the load side incident energy will be reflected in the ArcFlash labels that you print for certain panels. Which panels? For those that have a main overcurrent protection device. Okay. So this is probably the most important option that you have to be aware. Any electrical equipment that has a main overcurrent protection device, like here, let me put a little indicator that you will be able to see better my cursor. This is a main overcurrent protection device for a switchgear or switchboard. Okay, and if we have a main in not only a switchboard or a switchgear, but in a power panel, in a motor control center, in a lighting panel, whatever, if you have a main protection device, overcurrent protection device, you have two different values of ArcFlash incident energy. One at the line side, as we see here the incoming wires to the switchboard, and another one after the breaker in the load side. So they're two different values. Sometimes they are the same, but a lot of the times, this value on the line side is much, much greater than the value in the lines in the load side. So line side is much greater than in the load side. And here, don't get confused, even though normally you have line coming in and in the upper side and load side on the lower side. That's not the case here. The incoming lines are from below. So this is the line side and this is the load side, okay? So when working on the incoming section, and I am putting the incoming section here of the switchgear, which is where the incoming of the conductors and the main overcurrent protection device, that's the incoming section. When working on that incoming section, you could have an ArcFlash located before the breaker, right there. That's called a line side arc, okay? And the result of this will be substantially different than if you have a arc at the load side of this breaker, okay? In the line side, when you have an ArcFlash in the line side of the overcurrent protection device, this main overcurrent protection device will not even know that you have an ArcFlash. Well, yeah, you know, because there's still going to be some contribution for motors going to this point, but it's going to be much less, and it's really not going to help you with the majority of the energy that is coming from the utility from here. Okay, so the great majority of the energy you're going to see when you have an ArcFlash event in the line side is going to come from upstream there. And this circuit breaker does not help you to isolate that fault. And therefore, you're counting on a larger, maybe slower upstream device up here to open the fault. Maybe you have a transformer here, and between the transformer and this switchboard, there is no protection. So you have to go up to the primary side, in order to obtain that, that protection with a fuse in the primary side. So it might be much slower than if you have an ArcFlash at the load side. Okay? Now, here is a typical area where you could have an ArcFlash, and that's in the incoming section again. And if you calculate the arc flash in this line side, you could have, let's for example, 44 calories per centimeter square, and that could create a very dangerous situation. So dangerous that normally after at 40 and over, it is not permitted to work on energized panels because of the great amount of energy that you can have in this area when you have more than 40 calories per centimeter square. Very, very dangerous situation. Now, how about if you have an arc event at the load side of this breaker here? Well, in that case, the circuit breaker that the main overcurrent protection device will be in the path of the majority of the fault, of the majority of the energy. And this breaker could substantially reduce the time of opening due to this large arcing current here. So this breaker will see the arcing current and will open. Will not wait until the upstream device, will not wait for the upstream device to open. It's going to open faster probably than the upstream device. And the load side arc flash energy might be substantially lower than the upstream energy, okay? So that would be the case that you have an arc flash in any section of the switchboard after the incoming section, correct? So you have an arc flash here or here or here or any other section. You will be able to this breaker to open. Therefore, the incident energy here might be 5.81 calories per centimeter square instead of 44. Now, where this value, that's a real example. That's a real ArcFlash study that we have done, and this is pretty much the difference that we have in between the line side ArcFlash incident energy gives the result that you cannot work in this panel, and the load side incident energy that is a much lower energy and it's very workable. Okay. Now, how about if you have here 44? So you say, well, I cannot work in this incoming section, but in all the feeder section, I have an energy of 5.81. So I will never work in this section, and I will, but I will work in the adjacent sections from the incoming section because they have a lower incident energy. Well, that could be the case, but remember that if this cover is closed, where the arc flash can occur in the incoming side with a very dangerous energy, and you're working right by the adjacent section and having all this cover open, and if there is a open frame construction, in other words, that this switchboard between the sections, it's open, so you can see through, you have big holes. So all this energy that is very close, like when you are working here, can propagate to this section, and now you might have more than a 5.81. You might have less than 44 because you have a larger distance, but it will be probably more still. This energy that migrates to this place where you are located probably is much greater than 5.81. How much? Well, we have not done that calculation. We have done the calculation on the line side and the load side. And we have done this calculation at the line side only at the working distance for this panel. This will be greater than the working distance, and we have not made that calculation. If you want to make sure what it is, then probably you should make another calculation here with a different working distance. And then you will know for sure what is the incident energy. Of course, very few people do that, if any, okay? So it could be kind of interesting because if you're working this panel with very low PPE requirements, thinking that it's a real 5.81, and then there is an arc flash here, and you have a lot of energy propagating to this state, that makes the PPE that you had before useless, you may be thinking, which procedure will I have in order to consider this line side and load side options. Here we can see the barrier. There is no barrier between the incoming section, completely open, okay, and this is a feeder section that is right by the side. This is the feeder section adjacent to the incoming section, and everything is open, not only in the front, but you might be also open on the back. So it could be back and open, back and front, totally open, open frame. A lot of the older switchboards are like that. There is no barriers between the adjacent sections, okay? Let's see, this can happen not only in switchboards, but also you have the same situations with control panels. This is a control panel, and you have a main overcurrent protection device, and you have here a very small portion, which is the incoming section. And when you calculate the arc flash here, it might give you a value. When you calculate the arc flash after the breaker for the rest of the section, it gives you another value. The probability is that this value is going to be much higher than this one. So which value you would assign to this whole panel? You could say, well, I would assign the lower value, and I prohibit anybody to make an arc flash in the line side. Can you control that? How about this guy's working on this breaker, tightening some contacts, connections, and makes an arc flash right there? You don't have any barriers to protect the line side arc flash incident energy with the load side. So definitely, if I would be you, I would consider the worst possible case, that is the line side for the whole panel. Power panels, also they're open. You can have a main, and then you can have a lot of feeder or branch circuit breakers, a main breaker, and in this case, a whole bunch of branch circuits, branch breakers. If you have an arc flash in the line side, everything is totally exposed. You don't have any barriers when you're working on the load side. So large areas in panel without barriers, any panel that has large areas without barriers between the incoming section and the feeder or branch section, you're going to have that situation. Consider the line side flash incident or the lower. Motor combination starters, again, they have the line side and the line side and the load side. Which one are you going to do? Normally this is much higher than this, and there's no barriers to protect you if you're working with lower PPE in the low side when you have an arc flash incident in the high side. Now, what happens if there is no open spaces? If there is, the incoming section is insulated by steel from the adjacent feeder section, will this separation suffice to prevent the higher arc flash incident energies from the incoming side to migrate to the feeder section, especially the adjacent section? Okay, that's a good question. Well, that's the question that IEEE standard also is tackling, is addressing in standard that you see here, C37-20.7. Okay, and this standard is for testing equipment switchboards, switch gears that are supposedly arc resistant, resistant to internal arcing faults. And a switch gear that is resistant to internal arcing faults, you can have that resistance to the outside world. In other words, when you have an incident, an arc flash incident inside the panel, that energy is not going to migrate outside. In other words, the external barriers of steel are big enough, high enough, efficient enough not to let escape any energies out of the panel, burning or injuring the worker that is standing at the, in close proximity to the panel. So if you want to make sure that any energy will not migrate to the worker that is standing outside during an arc flash event, you can buy switchgear equipment that has been approved by the IEEE not approved, but that has gone through the test of the IEEE that are dictated in this standard. Now, very good, you do have to understand the fact that the arc resistant switchgear is good for any energies abandoning the panel. In other words, to the outside. There is also a testing method to certify that the switchgear is also resistant or fire resistant or arc resistant for between adjacent sections. In other words, that a section, an arc flash in a section is not going to migrate to another section. So now you have inside installation, so to say, the energy is going to be constrained to a specific section and not migrated to the adjacent section. And also that this energy is not going to migrate outside of the panel. So you have different types of tests and certifications, okay? Now, this IEEE is good for the switchgears up to 38 kV, up to. So it does include 600 volts, okay? So if you have low voltage metal enclosed switchgears that you want to test and you want to certify as arc resistant, you can do it according to the standard because it applies to low voltage metal enclosed switchgear. And of course applies to medium voltage metal clad switchgear as well. Now, I was telling you that you have different type of certifications. If you have a suffix C, well, in the certification, what does it mean? The suffix C means that you also have insulation or arc resistance between all adjacent compartments, not only to the outside, but inside, all inside. So all your compartments are isolated from energies of arc flash in the adjacent compartment. Now, concerning that, what happens if you have an arc resistant switchgear? Would you consider in the adjacent sections the lower load side energies, or you will still consider the arc energies from the line side? Well, I would probably start considering the lower side because I know that there's not going to be any energies going from the higher energy to the lower energies. Non-arc resistant switchgear, they're not proven, they're not tested, and you could have propagation of that energy even though you have steel barriers, okay? Now, of course, if you have a steel barrier, even though it's not arc resistant, you're going to limit substantially the energies to the other adjacent section. You might not completely eliminate them, but definitely you are going to reduce them substantially because you still have that piece of metal dividing the adjacent sections, okay? So be aware that even if you have that steel, if it's not proven, has not been proven according to the standard, or have not gone through the test of the standard that we saw before, the standard for arc resistant switchgear, you might still have some energy migrating to the adjacent sections. So now that we have established the problem, we have to devise a solution, okay? And the question is how we're going to label the switchgear when there's not only the switchgear, the switchboard, the power panels, MCCs, and all panels that has a main overcurrent protection device. What option of labeling are we going to use? Okay? Are we going to use for the whole panel the line side energies, the line side, which might be dangerous, 44 calories, so therefore making the whole panel out of bound for maintaining while it is energized? Or we're going to have another option, which is maybe in the line side, I put a danger, and in the load side of that label, in other words, in all the other sections, I put a warning label with the 5.8, which is a much lower category. and hoping that if the guys are working in the danger side, they might not by mistake see the warning and think that that's valid for the whole panel. So definitely you would have to do some training there. Or you can go with another route saying, well, I will have a dual side label and I will put that in the bus side. Okay, there is a certain energy, that's the load side actually. It's only 5.8, but in the line side, it's 44. It's dangerous. Okay, and you put the label, you put the header of the energies that are higher. For example, in this case, the line side is dangerous, so you put the dangerous header. Don't put the warning label. So those are the different options, okay, that you may consider. But there's a question that you have to address. Which label or type of labeling are you going to use in this panel? Which option are you going to choose? The labeling option will depend on certain things. First of all, what is your criteria as a professional electrical engineer? Remember that your neck is on the line. If you're a professional engineer and there is a explosion, and that in the incoming, there is an arcing in the incoming section, and someone, a worker, is working on the adjacent section with a category 2, and it gets burned, you would have to do a lot of explaining, correct? How come you didn't consider that you had a line side and a load side, and that it was an open frame switchgear, and that you could have more energies than the 5.8, which is at the line side, at the load side. Now, also depending about the safety program policies of the client. You have to get them in consideration. What are the policies of the how strict are they? Okay. And also, it will depend upon specific circumstances of the equipment that you are dealing with. Maybe you have an arc-resistant switchgear. Therefore, you can have maybe a dual label or one label at the incoming section and another type of label in all the other feeders. It's up to you. Maybe the safety program says, even though it's an arc-resistant switchgear, I want to have a consistent labeling system, and I will always choose the worst possible case. So you have different options here and different situations, okay, that you have to consider. When you have when you make the decision of printing the label for that specific type of equipment. Those were general recommendations, but now I will put my neck on the line and I will tell you what I do when I do ArcFlash studies. And this by no means has to be a standard, and this that by no means is going to be your truth. This is my truth, okay, and I believe on it. If I have a type S arc resistant switchgear, I definitely consider putting a dual label or two type of label with a lot of training, one at the line side and one on the feeder sections, okay? But make sure that you have a lot of training, understanding. Everybody has to understand that they have to check every panel when they're going to work to see if there is a main overcurrent protection device. If they're a main overcurrent protection device, they're going to see two labels on the panel. And they have to understand what those labels mean, what to apply, which section applies one label, which section applies the other, okay? If I have all non-resistant switchgear or resistant switch or arc resistant switchgear without the suffix S, okay? So I put them all together. If you have other arc resistant switchgear without the suffix S, or non-arc resistant switchgear, what are you going to do? Well, what I do is that I put the worst possible case label. So in this case, I will put the incoming section label or the line side. That's very restrictive for the customer. The customer might be limited not to work on some panels because you have chosen this route, but it's the safest route and the one that gives you less reliability and protects more the employees. But of course, handcuffs a lot of the maintenance procedures. Okay? So this is what I do in all the switchgear. This is a switchgear area. I follow that path. How about in power panels? I always consider the worst possible case. The worst possible case, which will be the line side. I will never put the load side energies. How about motor control centers? The majority of the motor control section, they have steel barriers between the different sections, but they're not rated to be arc resistance. I've never seen an arc resistant motor control center, especially with the internal sections, adjacent sections, that one ArcFlash event will not migrate to the other, proven by tests. There's actually no test for that for arc resistant motor control centers. So it's up to you. I don't like to take that liability, so I would choose the worst possible case, which will be the line side. I will follow the same thing with panel boards, lighting panels, also with control panels. I know this is kind of tricky with control panels because you have a small section where you have 408 volts. You have the incoming side line, you have normally a fuse or a breaker, and after that fuse or breaker, you probably have a transformer, step-down transformer that feeds all this electronics, okay, in this section of the control panel. And you have to sacrifice the whole panel because of a little section in the line side of the overcurrent protection device, of the main overcurrent protection device. But nobody can assure you that there is not going to be an arc flash at the line side of that overcurrent protection device. So in that case, I definitely put control panels as the worst possible case, which is line side. How about fusible discrete fuses? Well, this is kind of funny because it's not like a regular panel, it's just a fuse disconnect. Yeah, but you can calculate the energy before the fuse or after the fuse, correct? So I always, when I have a fusible disconnect or a single circuit breaker mounted on a box, which label do I put for that box or for that fusible disconnect? I always put the line side energy, which is the worst possible case. In 99% of the cases, there are very weird cases that I have found that the load side energy is larger than the line side energy. And those happen when you have, for example, maybe tie breakers where the main overcurrent protection device does not see the energies coming from big motors downstream and from tie breakers, from other switch gears that are tied to this bus and through tie breakers or tie switches. Okay. Now, kind of to finishing this option of considering line side or load side, or even sometimes you have software that you have to choose whether you are going to make the calculations on the line side or at the load side or both. So that's an option that you have to take even for software, okay? This is what IEEE 1584 says about all these panels that have a main overcurrent protection device. Note that if an arcing fault can be initiated on the line side of a main, and you think that arc fault can be initiated on the line side of a main all the time. Faults can be initiated on the line side of the main all the time. On the main line of protected device in an enclosure, that protected device should not be utilized for the calculations. Should not be utilized for the calculation. In other words, they are hinting you to the idea that it might be a much better situation to calculate that at the line side, not at the load side. Instead, the upstream protected device should be used. One, the one that is above that main overcurrent protection device. That is because only an upstream protected device can be considered to provide protection for an arcing fault on the line side of the main protected device in a downstream enclosure. Well, I think that's very clear to me. I don't know if it's clear to you, but it is for me, and that's coming from the mouth of the lion itself, IEEE standard 1584-2002. enough for line side versus load side. Let's go to some interesting situation here, which is arcing time. Every time you calculate arc flash incident energies, you have to make a decision on a very important variable, is the arcing time. A lot of time, you don't have to be concerned about the arcing time. Use putting it on like a number. Why? Because the arcing time depends on the arcing current and on the protection device that is protecting against that arcing current. So you have devices that are very fast for an arcing current, and devices that are very slow for the same arcing current. So the arcing current should be determined automatically by the current, the arcing current, and the time current characteristics of the overcurrent protection devices. But this is what happens when you have a very low arcing current, okay? When you have a very low arcing current, the overcurrent protection device protecting you against that arcing current, which is creating the arc flash and burning everything, will take a long time to open. Let's say 1 minute. It would not be a very nice thing to be exposed to a 1 minute arc flash event. As you know, the energies that you are absorbing are integrated through time. So the longer you are exposed to a source of energy, the greater the damage is present there. You are absorbing more calories per centimeter square the longer you are standing in front of a source that is emitting that type of energy, which is thermal energy. It's like when in the shower, you can be at, you know, what, 60 degrees Fahrenheit under water for a long time, but you increase it to 220 and you just can be very little time. The longer you are, the more damage you get. Well, the same with the arc flash. So what happened when you have an arc flash event? If you have a very low current and it keeps on integrating, and we just consider the time that the overcurrent protection device with no limit, even if it's a minute or 2 minutes, I would say that a good portion of the panels are going to be dangerous, okay? Because of that accumulation or integration of energy. But in real world, when you have an arc flash event, there is a blast and there is a person that is scared. There are two things: a very scared person and very shocked person, and a very pushed away person by a blast. And both things are at the same time. In an arc flash, the person by intuition is going to be running away from the danger, running away with his own feet, jumping away, jumping back, protecting itself. And also the blast is going to impel him backwards. It's a big blast. It's like TNT dynamite blowing up inside the panel. So it's going to push him back. So the IEEE has found that if you consider a maximum of 2 seconds as a maximum arcing time, it will make a lot of sense, because in 2 seconds, or you either have run away from the situation for your life, for your dear life, or you have been pushed away by the blast sufficiently enough not to be considered that you're absorbing more energy, okay? So for those circumstances that are low arcing current, with therefore with long arcing tripping times, therefore you have to consider a maximum, according to IEEE, of 2 seconds, okay? It says, if the time is longer than 2 seconds, consider how long a person is likely to remain in the location of the arc flash. In other words, how about if a person is doing some work on bus duct or busways, and it's mounted on a genie, and there is a very little space that he can run away to. I mean, no space to run away, unless he throws himself to the vacuum in the air, okay? But then you have another safety problem. So it's restricted. So he cannot move away either by his own feet or by the blast. In that case, how much time we consider? Well, that's definitely the criteria of the professional engineer that's doing this calculation, okay? So when you have some unusual cases like electric equipment that is in a restricted space that you cannot really run away very fast, is restricted. In those circumstances, you definitely have to consider more than 2 seconds. How much more? Well, it depends upon your criteria, okay? It's a very touchy situation with a lot of liabilities, so you have to use your own reasoning there. You're not protected by the IEEE anymore with a written time, maximum time, okay? A person in a bucket truck or a person who has crawled into equipment will need more time to move away. How much more time? It's open-ended. It's your decision. But you have to be aware that the majority of the time at 2 seconds maximum arcing time is good enough for IEEE. And again, if it's good enough for IEEE, it's good enough for me. Okay, we said that. That's kind of a repetition from the previous one. Okay, how will affect the question? Now we understand the problem. How much it will affect this problem in the calculations? Well, the only way of knowing what is the difference of considering a 4-second, for example, or a 5-second maximum trip delay tripping time, or a maximum of 2 seconds trip time, we have to have that calculation made with those two different values, leaving everything the same. Okay, so here we have a bus. This is a bus that's not protected by a line sight, so there is no overcurrent protection device before the bus. This could be a panel, okay, probably a switchboard. The breakers, feeder breakers are pretty big, so it's definitely a switchboard. And we have here the case when you have a, let's take this little terminal panel out of the way. The trip time, it's covered perfectly well. Let's see, no, I cannot move the little panel. So you would have to tell me, I know that in this situation it's a trip time of, oh boy, I wish I would know. Probably 2 seconds. The upper side is 2 seconds. And this is 5 seconds. So I calculated ArcFlash in this first above case, a 2-second maximum arcing time, 2 seconds according to IEEE, and I said, well, I will make the change to 5 seconds and see what is the difference. When I calculate the ArcFlash incident energy at 2 seconds, maximum arcing time 2 seconds, the ArcFlash incident energy is 18.6. Okay, when I calculated 5 seconds, it went 43.57. So it's a huge increment of energy because of the extra 3 seconds. So the arcing time, maximum arcing time, will give you an incredible amount of difference in your result. The same as the line side versus load side option. The maximum arcing time option, you have to have it very clear, spend time and effort, because it will give you a very big change in result. I remember that I was doing an ArcFlash. I was being questioned about an ArcFlash. I'm sorry, I'm still with a cold in all the week. And I went to do a consulting for a copper mine in Chile, where I was born. Santiago, Chile, I was born. And they invited me, some Phelps. There was a copper mine, La Candelaria, and they had some questions about a ArcFlash study that was done to them, and there were everything was pretty much dangerous everywhere. And guess what? What was the maximum arcing time? The person had not changed the value that was there put by default at that time, I don't know, it was 9999, 9,999 seconds. Can you imagine why everything was dangerous, okay? So here's the big difference. A very lower category with a very low incident energy, well, kind of low incident energy, and a very high incident energy just by adding 3 more minutes into the equation. Now, how about motor contribution? This is a very interesting subject. Motor contribution, how this option that you have to choose when you perform an ArcFlash study, include motor contribution, do not include motor contribution. Include motor contributions of motor greater than 50 HP, include motor contributions for all motors, even less than HP, etc., etc. Okay? How long to include the motor contribution? If you have induction motors, how long you have to include that contribution? If you have generators, and if you have synchronous motors, how long to include that contribution? Okay, well, here are some tips. Induction motors contribute according to their sub-transient reactance. That X with those 2 little wiggles to the right, okay? And that is only for a few cycles. Remember that the impedance of motors, it's a dynamic impedance. It changes with time. You don't have the same impedance for that motor. So if you have that motor acting as a generator, this induction motor acting as a generator during a fault, because the impedance changes from very low to very high, you have that contribution changing from very high to very low. And induction motors, in the beginning, they have a very low impedance called the sub-transient reactance. So they will contribute for a very few cycles, a very large amount of current, about 6 times their normal current. So if they have about 100 ampere of full load current, during the 4 to 6 cycles, the first 4 to 6 cycles after the fault, that motor is going to contribute almost 600 or more amps to the equation. Maybe that's the short circuit. Of course, it will be less for the arcing current normally, but still will contribute a substantial amount of arcing fault. Okay. Now, synchronous motors are a little bit different because they can contribute for longer than 4 to 5 cycles. They can contribute in different regions. They have the sub-transient reactance, like the induction motors, but also they have the transient and then the synchronous reactance. When you are dealing with contribution motor contribution, I should say, synchronous motors and generator contribution to arcing currents, you are dealing with 2, the sub-transient reactance and the transient. The synchronous reactance is valid after 2 seconds, okay? But we have already established that the maximum arcing time is going to be not over 2 seconds. It's going to be 2 seconds. Therefore, what sense is to model the synchronous reactance contribution when this is valid only after the 2 seconds, okay? So you're going to be dealing with the sub-transient and the transient reactance. So when you are dealing with a synchronous motor, the sub-transient reactance will be in for about 0.1 second, which is 6.25 cycles. And the synchronous reactance, or the transient reactance, will be up to 2 seconds, from 0.1 to 2 seconds, okay? And of course, you will not include the synchronous reactance because it's only valid after the 2 seconds. All this, you probably are doing the calculations with, of course, ArcFlash Module from SKM Power Tools. Okay, that's what I do, at least. And you can establish a lot of these parameters in the software itself in the options section. You have to be aware that there's an options section. I believe that in other software as well, besides the SKM, but I know for sure in this game, where you can adjust these contributions according to your needs. Okay, so there's options that you have meet, to decide which options you want for contribution. So as the ArcFlash incident energy will depend on the voltage fault current. That will definitely depend on the voltage fault current, because actually it depends directly upon arcing current, but the arcing current will depend upon the voltage fault current. Therefore, the ArcFlash incident energy depends on the voltage fault current. Contribution from synchronous and induction machine must be included in the voltage fault current to get more accurate results for ArcFlash incident energy. So that's my take. My take is, since ArcFlash incident depends on voltage fault and contributions are part of that voltage fault, they should be considered as a general rule. But we really would like to have a way of quantifying how much they will influence the result. That would be neat, to make a study, an investigation, and finding out how much the voltage currents from contributions will affect the ArcFlash incident energy. Okay, which we will do after a couple of slides. When you consider the motor contributions, there will be a high voltage fault. The higher voltage fault will generally result in a higher arcing fault. The higher arcing fault, due to the inclusion of motor contributions, not necessarily mean a higher incident energy. This is very important, this last paragraph right here. Even if you have higher arcing current because of additional motor contribution, that does not mean necessarily that you have a higher ArcFlash incident energy. It could be lower or it could be higher, and you really do not know until you do the study, perform the study. Okay? Now, when will be higher? How about finding out which circumstances will produce a higher ArcFlash incident energy when you have a higher arcing fault? In other words, when is going to be higher the incident, or the panel will be more dangerous when we consider the contributions for motors? That is when the arcing current that was present without the motor contribution, was already in the instantaneous region of the breaker. If you are already in the instantaneous region of the breaker with the original arcing fault, original meaning without the motor contribution, definitely you're going to be in the same region with higher contribution due to the higher arcing fault with the additional contributions of motors. So the time will not change, but you are having higher arcing currents due to the contribution. Why the time is going to be the same? Because when you're in the instantaneous region, no matter what is the current, the breaker is going to take the same time to open. So now the time is the same with the lower arcing current than with the higher arcing current, which includes the motor contribution, and therefore, since now you have a higher current and the time remains the same, you're going to have a higher ArcFlash incident energy. How many times the energies, I should say the arcing current without the contributions are already high enough to be in the instantaneous regions of the breaker? Lots of times. So in those lots of times, you're going to have higher energies with the additional contribution. How much? So once we have established that, there's a question: how much will this increase be? We really cannot know until we perform the calculations. We would be interested to know, for example, if we consider the additional arcing current due to the contribution of motors, if we could jump from one category, from one PPE requirement from one to another, to a higher one. That would be an interesting question. We're going to analyze that. If it is, I think that you should consider having the motor contributions in the system. As a general rule, the influence of motor contributions on the results of the ArcFlash incident energy are relatively low. As a general rule, are relatively low. So if you need to spend more time and money in other options, I would recommend that than taking a lot of effort documenting a whole bunch of motors. Because if you create a big effort in surveying motors in the field in order to include them as an option in your calculation, you might be spending so much more money getting these results, and the results on the ArcFlash incident results will have just a moderate effect that it might not be worth it. Okay, that's a point that you have to consider. On the other hand, what happened if the arcing, what happened now in the opposite side? What happened, for example, if the tripping time diminishes due to the large arcing fault currents? The tripping time diminishes because you were not, for example, in the instantaneous region of the breaker. This is the other option, the other situation, that the arcing current without the motor contribution was not in the instantaneous region, was in the overload region, and now you have a higher arcing current. Definitely, you're going to have less arcing time than before without the motor contributions. So can we now assume that since we have less time, with more current, we're going to have less energy? No, the only way to do this is performing the calculations, unless you're a genius. I guess if you're a genius, you wouldn't be able to figure out without doing the calculation. But you will never know the outcome, because there are two things competing when you include the motor contribution. One is higher current and the other one is lower time. Which one will win? I don't know. I do not know. I just do the calculations, okay? It is necessary to include the motor contributions? I would say yes, because if you have them already in the survey, and it's a matter of just adding them to the database, it might be worth it, the extra effort, to include all motor contribution, okay? And model them very accurately, because there might be some jumping of categories when you include the motor contribution, as we're going to see in a typical example in a couple of slides. Okay. Even though this magnitude of the change might depend on the specific case, it sometimes is very few times will jump from category, but the majority of the time will remain a low change, a low quantity change. We're going to here consider a specific situation that is one project that is typical industrial project. This typical industrial project, I named it, or is named plant, okay? And why it has a name? Because I got it from the SKM sample project called plant. So I ran this study. If you have Power Tools for Windows and you have the ArcFlash module, you will be able to run it and test it yourself as well. In this plant project, there is 875 horsepower of motors that are 480 volts, okay? But not only that, you have these are induction motors, obviously. But also there are some other induction motors at medium voltage, which is 4.16 kV, and we have many more HP. We have 13,500 HP at this voltage level of induction motors. Now, we have also a whole bunch of synchronous motors at 13,800 volts, 9,000 HP. And we also have small synchronous motor at 480 volt of 500 HP. So it's kind of a broad sampling of different type of motors and synchronous motor, induction and synchronous motors. And we're going to do some calculations and see what is the effect on the ArcFlash incident energy. We're going to include them in the calculation, then we're going to exclude them, and we're going to compare what's going on, okay? Okay, in this specific case, because I think we have to be very careful here not to make a general conclusion based upon this example. This is one example of million. And I truly believe that it is very difficult to make a general rule when talking about motor contribution, except that it does not increment substantially or it's not change substantially the energy. And if you want to save some money in the survey, you might want to be surveying larger motors only and leaving smaller motors like fractional horsepower and 10 HP motors more on the side, okay? Okay, let's see the results of this very specific case. There was, in this plant project, there are 35 locations, okay? When we did not include the motor contributions, and then we include them and compare them, there were only 24 locations had, well, not only, the majority of the locations, because there are 24, had slightly lower ArcFlash incident energy without the motor contributions. Okay? And without the motor contribution, 2 of those locations changed to a lower HRC with respect to having the motor contributions. That's what happened with this particular situation. Out of a total of 35 locations, 4 locations had slightly higher ArcFlash incident energy without the motor contribution, which is interesting. So it can go up and it can go down. And one of these locations changed to a higher HRC value. And out of total of 35 locations, 7 locations did not change even without motor contributions, okay? So 2 locations changed to a lower when without the motor contribution, and 1 location changed to a higher without the motor contribution, okay? So that's, in this particular case, was this change substantial? Well, if you are a person that is an electrician working on an energized panel, and it happened that with the motor contribution, it went in those few panels that went up 1 PPE category, you might be affected. You would like all motors to be included, okay? But again, you have to be reasonable, because a lot of these calculations, they are assuming a lot of stuff. We're assuming distances. And we're going to see the distances. When we assume them wrong, we are giving some type of error into the system. And we have to accept that error. The same with the motors. We have to, if we do not accept some type of error measurement in these calculations, we will never be able to do the calculations. It's better to have something than having nothing, correct? The trend of these results apply only to this particular case. This is a disclaimer. This trend might change considerably with other system parameters and system topology. You do not know how the ArcFlash incident energy will change until the calculations are performed. Okay. Okay. Current limitation, but it is already 10 o'clock or a little bit after that, and we have to take our little break. So we're going to, after about 5 minutes, we're going to come back and talk about this option number 4, which is current limitation. Should we consider the option of current limitation in our calculations, okay? So see you in about 5 minutes. Okay, let's see if everybody is in attendance. There are a couple of you still that are not, they're still in break. I might be able to wait for 1 more minute or less to come back on board, but not more than that, okay? Now, if you're thinking on some questions, there is a panel at the control, there's a section in the panel, in the GoToWebinar panel, and you can ask questions there. You can write them down if you want to. We might be able to get them at the end of the seminar, or if you want to, at the end of the seminar, raise that little hand that you have in your control panel. Also, you can, in that way, ask questions. Okay, it seems that everybody's back. We can proceed with the presentation. Let's talk about how the current limitation feature in the ArcFlash works, okay? Current limitation feature. As you know, the ArcFlash incident energy will depend on the arcing current. And not only upon the arcing current, but mostly on the clearing time of the overcurrent protection device. So, if we have a current limiting overcurrent protection device that will limit the arcing current and the clearing time, we will have lesser of an ArcFlash incident energy than otherwise, that a non-current limiting device, fuse or breaker, okay? So the current limiting overcurrent protection devices, can greatly influence your calculations, depending upon the value of the arcing current. If the arcing current is low, that is below the threshold of current limitation, below the moment or the current that the overcurrent protection device becomes current limiting device, because a current limiting device is not current limiting at all values of current. Only starts being a current limiting device when the current exceeds the current limiting threshold, okay? So if the arcing current is above that current limiting threshold, yes, you're going to see a substantial difference in the ArcFlash incident energy, and I mean substantial, not little, substantial amount of difference between a non-current limiting device and a current limiting device for the same amount of arcing current. Okay, so my recommendation is, yes, definitely consider the current limitation of current limiting devices. How can we consider the current limiting effect of, let's say first, of fuses? And remember, not all fuses are current limiting. There I still see some old designed fuses, like one-time fuses, okay? And even renewable fuses I still see sometimes, which are very old design fuses, 50 years ago or so, and they are not current limiting. So we're talking about here modern fuses, like the Busman the Busman RK5s and RK1s, FRSRs, the better ones are the LPS RKs, which are the current limiting fuses, the yellow fuses from Busman, okay? So when you are calculating ArcFlash incident energies with current limiting fuses, you have definitely some options. In this case, two options. First is considering the IEEE equation, the current limiting fuse specialized equations that are in section 5.6 of the IEEE 1584. Now, these are specialized equations that only apply to class L and RK1 fuses, not anything else, okay? If you have class J fuses, if you have class RK5 fuses, like fuse transfer busband, FRSRs and FRNRs, you cannot use these equations because these equations are specific to only class L and class RK1 fuses, okay? So you have that option of using the specialized fuse equations instead of using the time current curve to determine the arcing time of the fuse, and of course applying the normal equations from IEEE standards. Gentlemen, we had a little glitch in the system. I would like to, we're back, I'm sorry. We have a little challenge here with the system, but we're back. It should not be any problem from now on. The organizer, I would like you to give me a description of where we stopped. Where were we? We were at this slide. Are we at this slide? Can we start over at this slide? The organizer, you tell me yes or no with the chat box. The organizer, can you please answer me in the chat box if yes or no? Okay, there you are. There we are. We're sharing the screen now and tell me yes, that's the point. Okay, perfect. So let's start the presentation from this current slide. Okay, we'll briefly explain what I did before. The current limitation effect will limit of overcurrent protection device will limit both, you know, the arcing current and the clearing time. So it is convenient to use the current limiting effect of overcurrent protection device to do this calculation, for the calculations. It's very, very important. Okay, so let's go to the second slide after this, and how we're going to consider, now that we know that it's very important to consider the current limiting effect of fuses, then we need to know how to do it. Well, we have pretty much two ways or two options to consider the current limiting effects of these fuses. Okay, the first option is to use the IEEE 1584 equations. Okay, and these equations are in section 5.6 for current limiting fuses. Okay, this is very important to understand. These equations are only used for class L fuses and for RK1 fuses. So if you have any other type of fuses, like for example RK5 fuses, you should not use this fuse equation. These are specialized fuse equations, and they are not the standard IEEE equations. So these are specialized, and these equations will be accounting the current limiting effects of class L and RK1 fuses only. If you have RK1 fuses, J fuses, etc., you cannot use this method. The other one, let's say that we have a current limiting fuse and it's not RK1 and it's not a class L, but you would like to consider the current limiting effects, for example, of RK5 fuses. What should you do? Well, you can use the IEEE equations, but definitely you can do a second option. What is this? You consider a standard time. If the current, you consider that if arcing current is in the current limiting range or threshold of the current limiting fuse, you are going to impose a standard opening time of 1 cycle for that when the current limiting range of the fuse is achieved, or a quarter of a cycle. So you have two standard time, a quarter of a cycle and a half of a cycle. Now, which one to pick will be depending upon the magnitude of the arcing current. And let me explain this. In all this is a time current curve for a fuse, okay? And this is a current limiting fuse. From here on, you have the current limiting range of the fuse. From here and that way, you don't have a current limiting, you're out of the current limiting range of the fuse, and you have to use the standard equations for IEEE for calculating the ArcFlash incident energy. But what do you do after the current limiting range when you don't have any information about time on the fuse? Yeah, we don't have any current here to figure out the time. So, well, we say this following. You, assuming that where the fuse curve cuts the current axis, the x-axis, that's going to be a value of x. From x to 2x is a region, like we see here. And greater than 2x is another region, this one. In this first region, if the arcing current is in this region from x to 2x, you can assume half of a cycle, okay, of clearing time. If the arcing current is beyond the 2x, larger than 2x, you can assume a quarter of a cycle. Because the fuse, it becomes more current limiting with more, generally more current limiting after the 2x value, okay? So you can use that option. And that option then, with that value of time, then you enter into the standard equations for the IEEE equations, the standard equations with that time, that tripping time. And of course, you have already calculated the arcing time, and you have the variables then to calculate the ArcFlash incident energy. So that's a second way or a second option of considering the current limiting effect of fuses. Now, how current limiting circuit breakers? There are some modern breakers that are current limiting. That also the curve goes down and becomes faster as the current increases, and it's going to be a time where the curve of the current limiting breaker will also intersect the x-axis or the current axis. So how we can use the effect of current limiting circuit breakers for the calculation of ArcFlash incident energy? Well, IEEE 1584 has also specialized equations for circuit breakers, and those equations are in 5.7. But those specialized equations do not consider the current limiting effect of breakers. They are for standard breakers, all breakers. And the majority of the breakers are not current limiting, they're standard breakers. So you can definitely use the circuit breakers equation that IEEE gives you in section 5.7. But those do not include the current limiting effects of these breakers. So what should we do? Well, this is what we can do. We can use the same situation or the same methodology that we used for the fuses, the current limiting fuses, as the second option of the fuses. In other words, if we are in the current limiting range of the circuit breaker, between x and 2x of that range, we can assume half of a cycle. If it's greater than that, you can assume a quarter of a cycle, okay? So in that way, you have a tripping time of current limiting breakers in the current limiting range, and then with that time, you can plug it into the equations and calculate the lower flash incident energies due to the current limitation effects of current limiting circuit breakers. Very good. Now let's talk about working distance. Working distance has a very interesting effect on the calculation of ArcFlash incident energy. And we know what working distance is, and we're not going to be talking a lot about what it is, but how this working distance will have an effect on the ArcFlash incident energy, okay? The working distance obviously depends on two things: the type of equipment and its voltage. That's how you figure out the working distance for the ArcFlash incident energies. Why the working distance is important? Because we know that the further away we are from the source of the energy, we get less energy. The closer we are, we get much more energy. That's very intuitive. So of course, when we calculate the incident energy, we have to calculate it at a certain working distance. And there's some standard working distance, okay? And those standard working distance. So everybody can calculate the ArcFlash incident energy pretty much at the same standard working distances are specified in IEEE 1584. And here is an interesting thing that I would like you to realize. 15 kV, so this is medium voltage switchgear. The working distance is 36, okay? So it depended upon the switchgear, which is the type of equipment, and the voltage. Now, let's keep the same type of switchgear and lower the voltage. About 5 kV switchgear, the same value, 36, okay? Now, let's keep the same type of equipment, switchgear, but we change the voltage. This is low voltage, okay? Oops, it went down to 24. That means that you're going to be closer, if you are working on this energized switch gear, low voltage switch gear, you're going to be closer to the source of the arc. And that makes sense because at these other pieces of equipment, they are more massive, and all the bars and the exposed bars and connectors that can arc are deeper into the structure. So you are kind of further away from the source. But with low voltage equipment, you're much closer because they're thinner. They're not as deep. So for low voltage switchgear, so the type is switchgear and the voltage is low voltage, you have 24 inches for working distance according to the IEEE, page 9. How about if we change the type of equipment and we keep the low voltage? How about low voltage switchboard? low voltage switchboard. Well, all low voltage panels, except the switch gears, are all 18 inches. Interesting. So if you have a low voltage switch board instead of a switch gear, it's going to be 18 inches. And this is an important concept because when we do a survey, we have to have very clear if the survey, if the equipment that we're surveying is a switchboard or is a switch gear at low voltage, because that's different working distances. And if we make a mistake, that mistake could prove to be costly, okay? The working distance has an important impact on the results of the ArcFlash incident energy. So you have to consider this, the working distance option very clearly, very much. You have to consider it. On a typical low voltage switch gear, you have to consider the working distance as 24 inches. Let's see if that's true or not. I think that we have a little challenge. Typical low voltage switch gear, 24. Switch gear, yeah, 24 inches. If by mistake you consider the low voltage switch gear as a regular power panel, like a switchboard, low voltage switchboard, even though they look so similar, the result of the ArcFlash incident will be greater. So you're going to be, I guess, in the safer side because it's going to be greater. The ArcFlash incident energy at 24 inches for a switch gear is 2. The ArcFlash incident at 18 inches, which is for a switchboard, is 3.9. So it's higher. But at the same time, okay, it can go to, this is very close to jumping PPE requirements. Okay, especially if you have in your options to calculate the ArcFlash incident energy a high margin safety factor that if it's close, if the result is 0.1 calories per centimeter square centimeter, close to the next higher rating of PPE, you will jump into, in that case, you will be jumping to the next PPE requirement because you made a mistake in thinking that that was a switchboard instead of a switch gear, okay? The working distance for a low voltage switchboard is 18 inches. Only low voltage switch gears, this is the working distance of a low voltage switchboard is 18 inches. Only low voltage switch gear has a working distance of 24. So make sure you have that. The opposite could be even worse, that you have a switch board and you consider that it's a switch gear. If you consider it's a switch gear, then you might be in trouble, correct? Because you're going to be having a lower incident energy than what really is there. Okay, let's consider now something else. We have busways. In the industries, we have a whole bunch of busways all over the place. How we consider these busways? Because they are panels, they're kind of panels like this, but they are distributed in a long area. All this is a panel with breakers in a very restricted area. So all the impedances are pretty much the same. All the distances are pretty much the same. And therefore, we don't have any problem with impedances between this breaker and this breaker. They're all connected to a big bus, very short. But here, this bus could be extremely long. And the impedance between this breaker or this fuse and that fuse might be substantial. Or maybe between the first one, at least the last one, might be substantial. So how we calculate this? Well, we have to calculate the worst possible case, remember? And if we want to be exact in this calculating this ArcFlash incident energies at the bus, at each plug-in, and at each panel, we will have to have an exact impedance an exact equivalent impedance calculation. For example, here we have the feeder that is feeding that busway. This is the feeder that is feeding that busway. Then this is the first plug-in right there, okay, or the beginning, I should say, the beginning of the busway. There's a little bit of distance between the beginning of the busway and the first plug-in. The first plug-in, a little bit of distance, and therefore impedance. The bus duct or busway has impedance to the second one, and then another little bit to the third one, and so forth until we get maybe 100 feet away where we have a whole bunch of little plugins all along. Okay. Now, if we are exact, we have to know what is the impedance per foot in this busway, and therefore we can assign a number of the distance in this and the impedance per foot, and we will be able to have the impedance for this exactly, and so for the impedance for that, and so for the impedance for that. But that's not what we normally do in the field. That will create a lot of work. A lot of work. If you have the exact impedance, then no problem, because you will calculate the exact arc flash incident energy here, and at that bus plug, you could put a arc flash incident energy label, and this one will be different because as impedance, you would provide another label with a different result than this, and so forth, okay? And each panel you will place the correct label because you will consider this impedance plus this impedance plus this impedance, this plus this plus this for the load. This will be a different label because we'll consider this additional impedance that this does not consider, etc., etc. But that will be a whole bunch of work. Can you imagine measuring the distance to each plug-in, finding the resistance of this per foot of this busway, and then doing the division? It would take a lot of work, okay? So how about if we simplify the situation, and I would recommend you to consider 2 cases only, not 20 different cases, but 2 cases. And you pick the case that is the worst possible of the 2. Case 1 includes the total impedance of the busway. Case 2 assumes the busway with 0 impedance. So I have done a study of this, and unless the busway is extremely long, maybe more than 300 foot, you might have that the impedance, that the worst possible case might not be at the beginning or at the end, it might be at the middle. Kind of strange behavior, but that only happens when you have very long, not realistic busways. So I think that is even more than 500 feet. But for normal length busways, 150 feet or less, the worst possible case is going to be either the beginning, which means no impedance, okay, 0 impedance, or at the end, which means maximum impedance. So we can calculate case 1, where we consider that up to the first plugin, there is absolutely, this case 1 is we have all the impedance, the C1, the C2, the C3, that we're calculating if all the plugins are at the end of the busway. And then we calculate that value, and of course we calculate also the load, these panels, considering that this impedance is maximum. So we have a calculation here, and we have a calculation for each load. And we reserve that. We don't put it right away. We just keep that in mind. And then we take the case number 2, where we assume that all loads are at the beginning of the busway. All loads are at the beginning. There is no impedance. Of course, we calculate the arc flash here, and then the arc flashes at this panel. What we do now, we have those 2 scenarios. We choose which is the worst possible case. So we're going to have a worst possible case for a whole bus duct. So now we don't have an arc flash label for each individual plugin, but we have an arc flash label for the whole bus duct, and we have then one, of course, arc flash label for each individual panel, which is going to be different from the other ones, and it's going to be the worst possible case of the 2 scenarios. Okay. So that's the way that I recommend doing this. We have now a label placed in the busway every 15 feet, for example. Okay, that is going to be the maximum arc flash incident energy for all the plugins. And we're going to have at each panel its own arc flash incident label with the worst possible case scenario as well. So that way you can simplify tremendously this situation with the busway models, okay? What is the effect of distance? What is the effect of distance in the calculation of arc flash? Normally, the effect of distance is going to be gradual. In other words, if you increase a little bit the distance, you're going to have, it could be go both ways, a little bit decrease or a little bit increasing the arc flash incident energy. So normally, the rate of change of the arc flash incident energy is going to be comparable to the rate of change of the distance. But this does not happen all the time. Okay, let's see if we have a situation here that a very small change of distance, meaning 1 foot, can create a large change of arc flash incident energy. And here is an example. We have exactly the same circuit, exactly the same overcurrent protection device. This cable is exactly the same, except this is 481 foot and this is 480 foot. Okay? Now, we perform the arc flash calculations having both, of course, the same available short circuit current because they're connected to the same bus. And at this bus that has 1 foot more, just a slight change, you have a category 2. You have 5.28 calories. And this circuit that has 1 foot less than this, 480, is a category 0, which is 0.23 calories per centimeter squared. That's a huge change for only 1 foot, correct? Now, is this something that we have to be concerned? Well, first of all, we really cannot control this very much because when we are doing surveys, we're not writing down the length of the conductors with an accuracy of 1 foot. I can almost assure you that, okay? We don't have an instrument right now to measure the accuracy of any conductor length with that type of accuracy. We are just estimating the length. Sometimes it's a good estimation, and sometimes it's not such a good estimation, but we do the best, okay? And that's the best we can do. So we have to assume that there's going to be circumstances that we are going to have this type of situation, but they're not going to be very often. Why not? Because look at the distances, 481, 480. It's very strange that you're going to have a 90 ampere circuit with a distance of 481 foot to the bus. Normal, at least in an industrial environment, you're going to have this loads very close to the panel. That's why they distribute the panel. They have a panel, you have several power panels, at each power panel covering the loads of a certain area. So it's normal to have 30 foot, 50 foot, 100 foot, 150 foot, but everything over 150 foot is going to be probably fed by another power panel. So yes, you can have an incredible amount of change, and you have to be concerned about that. But remember that changes only occur when you have great distances, very long distances, okay? Here's another case, 245 feet, and this is the worst possible case when you have circuit breakers of 60 amps, lower than 100 ampere breakers, and you have 60 ampere breakers, and you have 245. Then you don't need a 400, but about a 245 to a 244 length for this particular case with this amount of short circuit current available, obviously. But still, runs are pretty long for a small breaker. So it's not really a common issue that you're going to find, okay? And why is that? Why just a small amount of increase in distance will give you a substantial amount of increase in arc flash incident energy? Because this is the situation. When you have the 480 foot cable, the arcing current is right here, okay? Very close to it's in the instantaneous area of the breaker, but very close to the overload area. By increasing 1 foot the impedance, you have lowered a little bit the arcing current. Now, it's really not in the instantaneous region, it's about in this area, correct? And in that area, of course, you have much more energy because the breaker takes longer to open than it would take otherwise. Okay, so that's the situation. So wires, about ending this effect of raceway, wires, you will not really have to be super concerned about the raceway effect there is a difference, obviously, between magnetic, or I should say metallic raceways and non-metallic raceways. You're going to have higher available short circuit currents with non-metallic, with non-magnetic raceways than you would with magnetic raceway, metallic raceways. So, but not all metallic are magnetic. So I talked about conduits, steel, magnetic conduits. So there's going to be definitely a difference, but that difference is going to be very substantial. And if you have to do a lot of survey and making sure what kind of raceway, the material of the raceway, you're going to have a lot more work to be done, especially in the survey and also in the data input. Maybe the first part of the run is a wireway. The second part of the run, it's a conduit, and then it ends up in another junction and it becomes a non-magnetic conduit. So one run could have 3 different personalities. It can get a little bit confusing. So I normally do not consider the effect of the raceways in the ArcFlash studies, okay? And here's an example. Either we have to finish as soon as possible to ask questions. Here we have the different ampere ratings, and we have the energies depending upon the distances. We have here, for example, let's take a 600 ampere breaker with magnetic conduit with different type of insulations. Even you can see the insulation, the difference of arc flash incident energy for the insulation of the conductor is almost non-existing, though there is a difference between magnetic and non-magnetic. For example, here is 0.87 and here is 0.79. It's a small difference, correct? That is at 300 foot. Now let's see the difference of a 600 at 50 foot, 0.92 and 0.93. So it's very, very low. I will not spend a lot of time. It's very difficult to justify the extra expense for that little result. Okay, so we have finished the presentation. I would like to know if anybody has any questions that I can answer. I will be glad. I will see if you have any questions here. Let me change my cursor. I will open the questions panel. There we are. I'm ready for your questions and answers. If you have a question, please raise your hand so I can activate your microphone. Or write it in the question panel. Meanwhile we wait, I would like to write in the chat box my telephone number in the chat box. Now you can see the telephone number. And I will give you my email. Where? So in the chat box, we have the email and my my telephone number for asking questions. Okay, there is a question I would like to address. Let's see if I can make this bigger. ArcFlash incident energy. If so, ArcFlash incident energy. If so, what practices do you utilize to double check ArcFlash calculation provided by utilized for? No, okay. They're asking me for a question. What kind of practices do I utilize to check that the results done by the ArcFlash incident, by the ArcFlash software? I use SKM software, okay? The result is do you come across many scenarios where the software doesn't correctly calculate ArcFlash incident energies? Not me. I have not come into scenarios that the software does not calculate the right incident energy. How do I know that without actually doing a calculation by hand? Because that would be the way to double check the ArcFlash incident calculations that the software gives you. It's calculating it by hand and compare them. I don't do that because I trust, first of all, that SKM Power Tools, the SKM system analysis software, which is the SKM, the Power Tools for Windows, it's a professional program. They have utilized the professional people to write the program. It's well respected. It's the largest software manufacturer available. And so far, almost all the results that I have given make sense. I have done this for a long time. I probably could figure out that something it doesn't make sense. Now, having said that, I have to tell you that several times I have found weird results. Like, for example, that the load side calculation is higher than the line side calculation. And I have found fault on the program. That's what I think. Oh, the program is faulty. But after making a very detailed analysis of the situation, I figured out that I was the person that was not utilizing or not interpreting the results in the right way, and the software was right. So that has increased the confidence for me that the software is giving me good results, and I normally do not double check the results, except that I see them and I see that if they make sense or not. I hope I answered your question, Andrew. If you have any other question, please write it down or activate the microphone. I wonder, Andrew, I am really curious to know which scenarios the program did not calculate the ArcFlash incident energy correctly. I would like to know that because I use this program extensively all the time for customers, and I've never seen that. So I'm curious to know which are the cases. If you can get a hold of me and we can analyze it together with, in another time, that would be fantastic, okay? That would be good for both of us. Okay, any more questions? I'm all ears here. I don't see anybody raising their hand. Normally people write questions. I think it's a good idea to activate your microphone, well, if you have one, and ask the question. You can always, if you're in the phone, you can always activate the phone, by the way. Okay, there is another question I would like to see. Did you use ETAP privilege for ArcFlash analysis? Let's see. I have used two software. I have used SKM much more. I have to recognize I'm very fond of that program. I started using it since it was DOS. So I don't even want to recognize how many years back, and I've been using it pretty much every day. I have used Easy Power. It's a good program too. I'm not that familiar with it. And I have not used ETAP. I'm sorry, if you have an ETAP question, I will not be able to answer it. I have my opinion about software programs. Of course, I'm biased toward SKM because that's the one that I most use, but I believe that all programs that are commercially available and respected, like ETAP, Easy Power, SKM, probably Sign, they are good programs with a lot of research and development and with good results. And so they will do the job, no matter which one you use. I think that the differences that I'm looking for good in the SKM, that give me very, very nice way of giving results, a very fancy, nice looking results with the software to the customer. So I can give them a very good impression. How do you look at different scenarios or options with SKM software? Oh, okay. Does it do automatically or you must manually change settings? Very good. Let's see if I can answer your question. But we have to go out of the presentation. So let me see if I can get out here. Open the software. We have we have a course on SKM how to do this stuff. We have very good courses, very practical, okay? So if you're interested more in the ArcFlash options and there's a course, I'm going to tell you, I'm not going to answer this question for you, but if you want more precise answers, you can do that by taking the options on the ArcFlash. Not the options, but the other one, the ArcFlash module, the ArcFlash module software, okay? Seminar. Okay, let's see. Let me get, I'm confused here by the screens. There we are. Okay, project, scenario manager. Here is where you create scenarios. So for example, we want to create a different scenario. So we're going to clone the first scenario, okay? We want to make all the changes. Let's see, change all. So we're going to create a different scenario. It's creating a different scenario. Exactly the same as the first one, okay? We have not changed anything. So we're in this different scenario. No, we're in the base project. So then we go to scenario manager and go to that scenario, okay? Activate and exit. So now we are in scenario one. We can change everything we want. So if we want to change things in the ArcFlash, let's run the ArcFlash for the scenario. And we're going to change different things, different settings. And therefore, when you calculate the ArcFlash in one scenario, it's going to be with those settings, those options. And when you calculate the ArcFlash in the base scenario, in the first scenario, it's going to have the other options, okay? And I would like to show that very briefly. To ask Saqer Khalil questions. I don't know if I pronounce it correctly. Let's see, here we are. So in this, we are where? We are in the scenario one. Okay, and in scenario one, we're going to write this with other options, this ArcFlash with other options. Okay, let's say that here we say we're going to consider all standard fuses, not current limiting fuses, which we shouldn't, but anyhow, we're going to consider the, let's see, what else? We're going to consider IEEE 1584, with voltages of less than 240, report calculations as 0. We're going to consider metric, calories per centimeter square, and we're going to consider non-metric, English, okay, and inches. And we're changing all the options here. We're going to consider this 4 seconds, the time at 4 seconds, the maximum marking time 4 seconds, etc. And then we calculate the ArcFlash again, okay? And all the results for this scenario, all the different results of ArcFlash for this different scenario are going to be obviously, in a lot of places, very different from the scenario number one, or the base scenario calculations. So that's where you can manually change all the settings for the second scenario. And you can have 20 scenarios. It's up to how much your computer can handle. Did I answer that correctly? Did I answer that question correctly? And this was the question from Andrew. I'm waiting for another question. If you want to raise your hand in the microphone or you want to write them down. Well. It's already the time, no more questions. I really would like for you guys to answer a brief questionnaire. It's just a brief questionnaire. It will take you 20 seconds to answer when you close this presentation. It's going to pop up in your screen. Please, if you're kind, answer that questionnaire for 20 seconds. It will make a big difference to us. In the meantime, I hope you have a fantastic day, and I shall see you in the next AmSafe webinar. Have a great day. Bye-bye.